So, we will learn first Faraday's laws of electrolysis, that is quantitative as well as qualitative aspects of products of electrolysis as well as amount of electrolysis. So, first one, Faraday's first law. So, according to this, the amount of the substance deposited at an electrode is directly proportional to the quantity of charge passed through the electrolyte. It means when you take any electrolyte, let us say molten sodium chloride, and when subjected to electrolysis, this is cathode through which electrons enter, and this is anode through which electrons exit. So, this is how happening, and at cathode reduction takes place. Reduction of the cations occur at cathode, that is Na plus takes up electron and will deposit as sodium. So, these sodium ions go there and capture the electrons and deposit as sodium metal. So, this is what sodium metal. So, this process is reduction. Wherever reduction occurs, conventionally we call it as cathode. Similarly, at anode, oxidation occurs. At anode, oxidation occurs. Oxidation of what? Anions. So, these anions will come to anode and undergo oxidation. Oxidation is Cl minus loses electrons and become Cl2 gas. So, here at cathode sodium metal is deposited and at anode chlorine gas is liberated. Now, according to Faraday's first law, the weight of the substance reacting at an electrode is directly proportional to the quantity of charge passed. Means how much current we are passing through, that will decide how much quantity has to be interacting at the electrode. For example, if you send one electron through cathode, one cation will go there, receive the electron, that means it undergoes reduction there and will deposit as sodium metal atom. Another electron if you send, another sodium ion will go there and will catch the electron, will deposit at sodium atom. So, as many electrons you send, that much sodium quantity is deposited. So, we know that 96,500 coulombs is nothing but 1 Faraday, and that is nothing but charge carried by Avogadro number of electrons, charge of Avogadro number of electrons. So, if I am passing through 1 Faraday of current through cathode, means I am sending 1 mole of electrons. So, all the 1 mole of electrons will deposit 1 mole of sodium ions and will deposit as sodium metal atom. So, Avogadro number of sodium ions will become Avogadro number of sodium atoms. Avogadro number of sodium atoms is nothing but 23 grams. So, when you send 1 Faraday of current, Avogadro number of sodium ions are deposited and you will get 23 grams of sodium is deposited. 23 grams of sodium is deposited. So, we say weight of the substance deposited is directly proportional to quantity of the charge passed. Here this is quantity of the charge measured in coulombs. Quantity of charge measured in coulombs, and this Q in coulombs is nothing but current strength in amperes and time in seconds. Current strength in amperes and time in seconds. So, we say W is proportional to I into T, and here when you send 1 Faraday, it is depositing 1 equivalent weight. So, when you send instead of 1 Faraday, if you send 1 coulomb of charge, 1 coulomb of charge, then the quantity deposited here is less, and that quantity we call as electrochemical equivalent. This is electrochemical equivalent. So, what is electrochemical equivalent? It is nothing but here proportionality constant we say W is equal to EIT, where E is called electrochemical equivalent. So, electrochemical equivalent is amount of the substance interacting at the electrode when 1 coulomb of charge is passed through the electrolyte, 1 coulomb. 1 coulomb we are passing. Then this electrochemical equivalent units grams per coulomb. Grams per coulomb. So, how many coulombs you are sending and how many grams is depositing, that is called electrochemical equivalent. And the relation between electrochemical equivalent and chemical equivalent. Chemical equivalent means capital E, we represent it as, it is nothing but gram equivalent weight. The relation between electrochemical equivalent and chemical equivalent we are going to find now. Now, a relation between electrochemical equivalent and chemical equivalent. This relationship we are going to learn, which is crucial. When you send 1 coulomb of charge, 1 coulomb of charge means relationship we know 96,500 coulombs is 1 Faraday. So, I am sending only 1 coulomb of charge, then you will get some amount of sodium deposited, and this quantity is very little quantity, small amount of quantity deposited. And if you send here instead of 1 coulomb, if you send 96,500 coulombs, means 96,500 times of more current you are sending. So, automatically that means you are sending now 1 Faraday of charge. When you send 1 Faraday of charge, 96,500 times of more quantity than earlier deposited will be deposited now. Means the quantity deposited here will be 96,500 times more than the quantity which was deposited earlier. Earlier is small quantity deposited, now it is large quantity deposited. This quantity is electrochemical equivalent and this quantity is chemical equivalent. And the relationship between these two is, this value is more, electrochemical equivalent is less, chemical equivalent is more. So, and the relationship is E is equal to 96,500 times of small e. Reason you know, this is due to 1 coulomb and this is due to 1 Faraday. So, this is from 1 coulomb of charge and this is due to 96,500 coulombs, that is 1 Faraday. Relation is E is equal to 96,500 times of small e, or capital E is equal to F into small e. This F is nothing but Faraday, 1 Faraday is 96,500 coulombs. So, according to Faraday's laws, we came to know weight of the substance deposited is EIT, and here in place of electrochemical equivalent, I replace it with chemical equivalent by Faraday, because small e is equal to E by F, EIT by F. This is weight of the substance interacting at an electrode is chemical equivalent, current strength in amperes, time in seconds, and F stands for Faraday. So, now we know chemical equivalent, that is equivalent weight of the substance, is nothing but its molecular weight by its valency. Molecular weight by valency is nothing but chemical equivalent, capital E value. So, here in place of E, I can write molecular weight by valency. So, M by Z into IT by F. Here instead, in place of equivalent weight, we write molecular weight by valency, I into T by F. So, this is Faraday's first law. Faraday's first law. And the simplified expression for Faraday's first law is, when you send 1 Faraday of current, every time 1 gram equivalent weight of the substance will be reacting. When you send 1 Faraday, 1 gram equivalent weight of the substance will be reacting. That is the primary rule, and based on that we can do lot of problems. Let us see how. Okay, this is Faraday's second law we are going to study now. What Faraday's second law state is, when you send same quantity of current through different electrolytes which are connected in series, like this. So, this is cathode, this is anode, and this is cathode for the second electrolyte, and this is anode. Now, connecting these two, we are sending same quantity of current through different electrolytes. Now, this is through cathode, we are sending electrons. Same quantity of electrons means I am sending, say, some 4 electrons I am sending through this electrolyte, which is having molten sodium chloride. Molten sodium chloride, I am not representing the chloride part here, only sodium part I am taking. So, this is sodium ions electrolyte, and this is magnesium ions electrolyte, that is a magnesium ions electrolyte. Now, when you send same quantity of current, how many sodium ions will deposit there? Each sodium ion plus 1 charge, it need 1 electron to deposit, and I am sending 4 electrons. So, you can say 4 sodiums deposit over there. So, the amount of sodium deposited is 4 sodium atoms. Now, the same 4 electrons will exit through anode due to anionic oxidation. Whatever is anion is there, that will undergo oxidation here, delivering the same 4 electrons. The same 4 electrons enter now through molten magnesium ions electrolyte. The 4 electrons will be received by Mg+2. Every magnesium plus 2, due to charge plus 2, it need 2 electrons to get deposited, and as I am sending 4 electrons, 2 magnesium ions will take 2 electrons each and will deposit as 2 magnesium atoms. So, only 2 magnesium atoms are deposited here, and same 4 electrons will deposit 4 sodium atoms here, 4 sodium atoms. Then coming to the quantity, if you speak, 4 into 23 is the weight in AMUs deposited. Similarly, this is 2 into magnesium atomic weight is 24. So, 2 into 24 atomic mass units, that is what the quantity deposited. And what Faraday's second law state is, when you send same quantity of current through different electrolytes, the quantities of the substances deposited will be in the ratio of their equivalent weights. Means, weight of the magnesium deposited is to weight of the sodium deposited. This weight ratio is in the ratio of their equivalent weights. So, that is equivalent weight of sodium and equivalent weight of magnesium, that is W1 is to W2 is equal to E1 is to E2, or else W1 by W2 is equal to E1 by E2. This is Faraday's second law. So, weights ratio is, you can check, 48 is to 112. 48 is to 112. And when you take the equivalent weight of magnesium, every magnesium is taking 2 electrons to deposit as magnesium. So, the N factor or the valency of magnesium is 2. So, what is the equivalent weight of magnesium? Equivalent weight of magnesium is its atomic weight by the number of electrons it is taking due to its reduction. So, it is by 2, that is 12. So, equivalent weight of magnesium is 12 and equivalent weight of sodium. Sodium is taking 1 electron to undergo reduction, means every 23 grams of sodium need 1 mole of electrons. So, valency of sodium is 1. So, equivalent weight is atomic weight by valency, that is nothing but 23, and now it is 23. So, the ratio of weights deposited due to passing same quantity of current, this is the weights deposited, and the weight ratio is exactly in the ratio of their equivalent weights ratio. So, simplifying this, you will get 12:23. So, that is what Faraday's second law, W1 by W2 is equal to E1 by E2. First law of electrochemistry, W is equal to EIT by F, and second law is W1 by E1 is W2 by E2. Yes. So, based on these two, let us think about some numericals and conceptual questions. We know 1 Faraday of current is nothing but 96,500 coulombs, and which is nothing but the charge carried by 6.023 into 10 power 23 electrons. Keep this in mind, and that is 1 Faraday, and 1 Faraday of charge when passed through any electrolyte, the quantity of the metal if deposited will be equal to 1 gram equivalent weight. If it is a gas liberated, that is equal to 1 gram equivalent volume of the gas. So, let us take sodium 23 grams, magnesium 12 grams, aluminum 9 grams, silver 108 grams, and copper. When comes to copper, is copper obtained from +2 oxidation state or +1 oxidation state makes difference. Suppose copper is from +2 to 0, then its equivalent weight is 64 by 2. Real value is 63.5, but in together we can take it as 64. So, 64 by 2. Suppose copper is formed from +1 oxidation state, copper is deposited, then its equivalent weight is 64 grams. Zinc is 66 grams, like this we can take. This is gram equivalent weight. Coming to non-metals like hydrogen, chlorine, oxygen, hydrogen equivalent weight is 1, chlorine equivalent weight is 35.5, and oxygen equivalent weight is 8. Here also oxygen equivalent weight is 8, but when it is from -2 oxidation state, if oxygen is coming, then valency is 4. Suppose if oxygen is coming from peroxide ion, this is oxide ion, this is peroxide ion, then the valency is 2. So, when oxygen is obtained from oxide compounds, equivalent weight is 8. When oxygen is obtained from peroxide compounds, equivalent weight will be 16. So, this should be kept in notice. Now, what is gram equivalent volume? We know 1 mole of any gas will occupy 1 gram molar volume. This gram molar volume is 22.4 liters. Similarly, 1 gram equivalent of any substance, if it is a gas, will occupy a volume that is called gram equivalent volume. 1 equivalent of any gas occupies a volume which is equal to gram equivalent volume under STP conditions. under STP conditions. Now, this is a gas and the equivalent weight of that is 1 gram. You know, molecular weight of hydrogen is 2. So, 2 grams of it will occupy 22.4 liters. So, hydrogen whose equivalent weight is 1 gram. So, 1 gram will occupy 11.2 liters. This is called gram molar volume of hydrogen gas and this is called gram equivalent volume of hydrogen gas. So, 1 gram is the weight of hydrogen in terms of equivalent weight and 11.2 is its gram equivalent volume. Similarly, chlorine molecular weight is 71 grams and that will occupy 22.4 liters at STP, whereas 1 gram equivalent of chlorine, that is nothing but 35.5 grams. So, 35.5 grams will occupy 71 is 22.4, 35.5 is 11.2 liters. So, this 11.2 liters is called gram equivalent volume of chlorine gas. Similarly, coming to oxygen, 8 grams. 8 grams means we know oxygen molecular weight is 32 grams. So, that will occupy 22.4 liters. 8 grams will occupy 5.6 liters. This is called gram equivalent volume of oxygen gas. So, this is what the information we should have in mind in order to do the problems. These equivalent weights as well as these 3 equivalent weights as well as these 3 equivalent volumes. Maximum will cover number of concepts. Let us see how these can be applied in numericals. When molten sodium chloride is subjected to electrolysis. Molten sodium chloride is subjected to electrolysis. Suppose certain quantity of current, some quantity of current I have passed, and that will deposit how much of sodium and will liberate how much of chlorine? That is my question. As per Faraday's law, first law, 1 Faraday will deposit 1 gram equivalent weight of the metal at cathode, and if it is a non-metal that is liberating as gas, that will liberate 1 gram equivalent volume. 1 gram equivalent volume. So, you know gram equivalent weight of sodium is 23 grams. Gram equivalent volume of chlorine is 11.2 liters. So, every 23 grams of metal deposited here will simultaneously make 11.2 liters of liberation of chlorine gas. 11.2 liters of chlorine will be liberated. So, this is the quantitative relationship between sodium and chlorine. 23 grams will simultaneously liberate 11.2 liters. Suppose I have sent 1 Faraday of current. 1 Faraday of charge if I have sent, you will get 23 grams of sodium deposited here, 11.2 liters of chlorine liberated here. Instead, I am sending 0.5 Faradays. 0.5 Faradays will make 0.5 gram equivalents of sodium, 0.5 gram equivalent volume of chlorine. 0.5 gram equivalent of sodium means 23 by 2 grams, because 1 gram equivalent is 23. So, 0.5 Faradays will be equal to 0.5 gram equivalents, that is 23 by 2 grams, and same 0.5 will simultaneously make chloride ions oxidation, resulting 11.2 by 2 liters of chlorine gas at STP. So, 0.5 will give 23.2 and 0.5 Faradays will give 11.2 by 2. Now, let us do one problem. the quantity of charge needed to completely oxidize 1 mole of permanganate to Mn+2 is how much? So, the options are 0.1 Faraday, 0.5 Faraday, 5 Faraday and 2 Faradays. How much of charge is needed for the reduction of MnO4- to Mn+2? So, here permanganate ion is reduced to manganese ion and the oxidation state of manganese is changing from +7 to +2, that is reduction, and the reduction is due to gain of electrons. So, +7 oxidation state of manganese takes up 5 electrons and becomes Mn+2. So, for 1 mole of permanganate ion we have 5 electrons, that is 5 moles of electrons. 5 moles of electrons is nothing but 5 Faradays is needed. So, for complete 1 mole of MnO4- to Mn+2, the quantity of charge needed is nothing but 5 Faradays. So, we should find the change in oxidation state and that will decide the quantity of charge. So, for 1 mole 5 Faradays, half mole 2.5 Faradays, like that any moles will decide the Faradays. The weight of silver deposited by a quantity of electricity which displaces 560 ml of oxygen at STP is. So, we are sending some quantity of current through an electrolyte which is liberating 560 ml of oxygen at STP, and that quantity of charge can deposit how many grams of silver? That is the question. Now, we know according to Faraday's second law, if you send same quantity of charge through different electrolytes, the quantities reacting at the electrodes will be in the ratio of their equivalents. So, that means 560 ml of oxygen is liberated by how many Faradays we should understand. According to our knowledge, 5.6 liters of oxygen at STP is the 1 gram equivalent volume, and for this much liberation of oxygen we need 1 Faraday, that is a fact. And similarly, silver we need to be deposited, that is 108 grams need 1 Faraday, because silver equivalent weight is also 108 grams. So, both are 1 equivalent, they demand 1 Faraday of charge. Now, we have got only 560 ml of oxygen. So, according to this relation 5600 ml liters I am converting. This is requiring 1 Faraday, and as per the reaction 560 ml only liberated, means 0.1 Faraday we have used. So, the current we are using, the charge we are using is 0.1 Faradays, that is liberating 560 ml of oxygen. So, with the same 0.1 Faradays, how much silver will be deposited? According to the rule, 1 Faraday will deposit 1 gram equivalent weight, and as we are using 0.1 Faraday will deposit how much? It can be stated that it is 10.8 grams. So, 10.8 grams will be deposited during 560 ml of liberation of oxygen during the process. So, answer is, so let us do one more problem which is based on Faraday's first law. See here, aluminum oxide is reduced by the electrolysis at low potential and high currents. If 4 into 10 power 4 amperes, current strength is 4 into 10 power 4 amperes of current is passed through molten Al2O3 for 6 hours time. So, the mass of aluminum deposited is, this is the question. Now, here current strength is 4 into 10 power 4 amperes. We know according to Faraday's law, first law, W is equal to E I T by F, and the equivalent weight of aluminum, as we know, aluminum is tripositive in this compound Al+3, and therefore it takes up 3 electrons to deposit as aluminum. So, the valency is 3. So, equivalent weight of aluminum is 27 atomic mass by 3, that is 9. So, we can substitute here 9 and the current strength in amperes, which is given as 4 into 10 power 4. So, it is 4 into 10 power 4 and the time is 6 hours of electrolysis. 6 hours we should substitute in seconds. So, 6 hours means 6 into 60 minutes into 60 seconds. So, this is altogether time taken for the electrolysis, and the Faraday is 96,500. 96,500. So, this can be simplified. So, cancelling zeros, and altogether we can write weight is equal to 9 into 4 into 6 6 are 36 into 6 by 965 into 10 power 4, and this upon simplification will give you the answer. Simplification will give you the answer. So, it is 8.1 into 10 power 4 grams. So, let us do one more problem on Faraday's laws. So, how many Faradays are required to reduce 1.23 grams of nitrobenzene to aniline? So, here nitrobenzene is undergoing reduction to aniline, and in that process for 1.23 grams of reduction of nitrobenzene, how many Faradays are required? So, here nitrobenzene is reducing to aniline, and if you see the oxidation states of nitrogen here and there, because remaining all will have the same oxidation state. So, the nitrogen oxidation state here is +3 and the nitrogen oxidation state here is -3. So, altogether a nitrogen oxidation state is changing from +3 to -3. So, from +3 to -3 is altogether 6 oxidation states difference is there, means 6 electrons are gained by this nitrobenzene in order to undergo reduction to aniline. So, according to this, for one molecule of nitrobenzene 6 electrons are needed for its reduction. So, for 1 mole 6 moles of electrons are needed. 6 moles of electrons means 6 Faradays. So, for 1 mole 6 Faradays are needed for the reduction of nitrobenzene to aniline, but we are not reducing 1 mole of nitrobenzene, we are reducing 1.23 grams of nitrobenzene. So, this 1 mole of nitrobenzene, if you calculate the molecular weight of this, will come out as 123 grams. So, for every 123 grams, that is 1 mole, we need 6 Faradays of current, and as we are reducing 1.23 grams, we need 0.06 Faradays of current, and according to this, third one is the answer. We will do one more problem which is based on Faraday's laws, that is valencies. Now, here the amount of iron deposited by passing 0.2 Faradays of charge through an electrolyte containing 0.1 mole of ferric ions is. So, we have an electrolyte in which we have ferric ions, and through this we are sending 0.2 Faradays of charge. 0.2 Faradays of charge we are sending through this, and as a result the ferric ions will be reduced here, and the ferric ions reduction leads to the deposition of iron. And his question is, how much iron is deposited by sending 0.2 Faradays of charge containing 0.1 mole of ferric ions. So, here we have 0.1 mole of ferric ions, and you are given the reduction potential values. Ferric to ferrous is 0.77 positive value, ferrous to iron is 0.44 negative value. What is the meaning? When you drive electrons, first ferric will reduce to ferrous ions, all the ferric will reduce to ferrous, and later the ferrous will reduce to iron. That is what the process. So, here if you take like this, so we have ferric, first it will reduce to ferrous, then it will reduce to iron. So, this is the reduction process. And ferric to ferrous, you know the charge is decreasing by 1 unit. So, this need 1 electron, means for 1 ferric to reduce to ferrous, 1 electron is needed. For 1 mole, 1 mole of electrons needed. So, for 1 mole, 1 Faraday is needed. So, this is 1 Faraday for 1 mole of Fe+3, but we have only 0.1 mole of ferric ions. So, taking 0.1 mole of ferric ions, for 0.1 mole of ferric ions, we need 0.1 Faraday only. So, first 0.1 Faraday is used up, out of how much? 0.2 Faradays. So, out of 0.2 Faradays only 0.1 Faraday is used up, 0.1 mole will be reduced to ferrous, and the ferrous obtained will also be 0.1 mole. 0.1 mole of ferrous ions are obtained, and out of 0.2 Faradays, 0.1 Faraday is already used up and remaining 0.1 Faraday only left. As per this reduction, 2 Faradays are needed because the change is +2 to 0. 2 Faradays are needed for a complete reduction. For 1 mole, 2 Faradays needed. So, for 0.1 mole, we really need 0.2 Faradays, but we have only 0.1 Faraday. So, this 0.1 Faraday can reduce only half of the existing amount of ferrous. So, 0.1 Faraday will reduce only 0.1 by 2 moles of ferrous into iron. So, the iron obtained will also be 0.1 by 2 moles. 0.1 by 2 is nothing but 0.05 moles of iron. So, first 0.1 Faraday is used up for the reduction of ferric to ferrous. Later, remaining 0.1 Faraday was successful to reduce only 0.1 by 2 moles of ferrous to iron. So, 0.05 moles of iron only we get. So, answer is 0.05 moles. Let us do one more problem on Faraday's laws. A 5 ampere current is passed through a solution of zinc sulphate solution, aqueous solution of zinc sulphate for 40 minutes. The amount of zinc deposited at cathode is. So, he is asking only amount of zinc deposited at cathode. So, we have to calculate. So, according to Faraday's first law, the weight of the substance deposited will be equal to EIT by F. E stands for chemical equivalent, I amperes, T seconds, F is nothing but Faraday. So, according to this, we know the equivalent weight of zinc. Here zinc is in +2 state and is going to be deposited as zinc 0. So, we can write the relation zinc +2 electrons gives rise to zinc, means during the formation of zinc 2 electrons are used up. So, its valency is 2. Therefore, equivalent weight of zinc is nothing but, let us say, 66 by 2, which is nothing but 33. Let us take 33. Now, according to this weight, the weight of the zinc deposited will be equivalent weight, that is 33, and the current strength we are using is a 5 ampere current strength. So, 5 amperes, and the time allowed for electrolysis is 40 minutes. We should take time in seconds, that is 40 minutes means 40 into 60 seconds. 1 Faraday is 96,500 coulombs. Simplifying this, we will get altogether weight is 4.065 grams. Simplification you can do, 6 4s are 24, 24 5s are, we can calculate, altogether will come out as 4.065. Yeah, let us do one more problem on Faraday's laws of electrolysis. So, the pH of 0.5 liters of 1 molar sodium chloride solution after the electrolysis for 965 seconds. So, the duration for electrolysis is 965 seconds and using 5 amperes of current, and the current efficiency is 100%. Now, what are the products of electrolysis? We should understand first. So, when you take NaCl aqueous, there is water also, and when you subject this for electrolysis, we get not sodium is deposited here, it is hydrogen liberated here due to its better reduction potential. So, hydrogen is liberated here, and here chlorine gas will be liberated, that is at anode chlorine gas, at cathode hydrogen gas are liberated, and as a result of hydrogen and chlorine gases liberation, what is left in solution is nothing but Na plus ions and OH minus ions. Altogether solution is becoming basic, and as a result of basic nature pH will be more than 7. So, out of those two, definitely either this will be the answer or this will be the answer, because the resultant solution will be definitely basic. Writing the equation NaCl plus H2O, when you subject it to electrolysis, you will get hydrogen gas liberated at cathode and chlorine gas liberated at anode, and sodium hydroxide is formed in solution. So, we know 1 Faraday of current always deal with 1 equivalent of the electrolyte. So, we have one more, 1 Faraday is always related to 1 gram equivalent weight of electrolyte or 1 gram equivalent volume of the gas. So, here we have 1 mole of NaCl in 1 liter, 1 molar means it is 0.5 liters. So, the number of moles of NaCl is nothing but molarity into volume in liters, that is 1 into 0.5. So, we have 0.5 moles of NaCl, 0.5 moles of NaCl. So, here we have 0.5 moles, and out of 0.5 moles, how much is undergoing electrolysis is decided by the quantity of charge we are sending. So, quantity of charge is what? So, according to this time and amperes, quantity of the charge is 5 amperes we are sending for 965 seconds. So, this 965 is nothing but 0.01 Faradays. So, altogether the Faradays is 5 into 0.01 means 0.05 Faradays of charge we are passing. So, 0.05 Faradays of charge when we pass, out of this the one which is undergoing electrolysis is 0.05 equivalents. So, because of 0.05 Faradays, 0.05 equivalents of NaCl will undergo electrolysis, and that will produce 0.05 equivalents of NaOH. So, this is what NaOH we got in electrolyte, and the electrolyte quantity was mentioned as 0.5 liters. So, 0.05 equivalents is produced in 0.5 liters. So, the normality of this NaOH we can calculate. Normality is nothing but OH minus ions concentration, which is 0.05 equivalents out of 0.5 liters. So, this upon cancellation we get 1 by 10. That means, OH minus ions concentration is 10 power minus 1. OH minus ions concentration 10 power minus 1 implies POH is equal to 1. POH is 1. So, automatically we can say pH, which is nothing but 14 minus POH, that is 14 minus 1, which is equal to 13. So, the answer is 4. pH of the solution will be 13. So far మనం Faraday's laws of electrolysis in electrochemistry నేర్చుకున్నాం. So final thing ఏంటంటే every time you should keep in mind that how many Faraday's of charge you are using, and as a result how many gram equivalents of metal if deposited you have to calculate, or if it is a gas liberated how many gram equivalents of gas is liberated, that is in terms of volume we can calculate. Both Faraday's first law and second law deals with quantitative estimations during electrolysis.